but hand the floor to Michael, who's been so kind to fill in last minute for a late cancellation. Thank you very much, and the floor is yours.
Thanks. Hi, everyone. I'm Michael Bologna. I'm a principal consultant at Great Lakes Consulting. We're a US-based consulting company that uses Julia primarily for web application development, for machine learning, scientific machine learning, and plenty of other fun. So let's talk about a fun problem. But now the year is 2015. We're working on a patient finance healthcare application that has already been in production, but in a smaller form, smaller scope of work. And so we're trying to expand the data sets, increase the amount of value we're getting from our data by doing filtering, aggregations, joining in memory for a finance team to try and understand their data better, trying to make good decisions. So these data sets are 100 plus columns. They're 30 to 50 dimensions, and then each of those dimensions, there's measures described in each of those, and so the data sets can be upwards of 10 gigabytes. And not only do we have just one data set in memory, but we're working with a bunch of hospital systems and different kinds of models. So now we're thinking about many of these data sets that can be up to 10 gigabytes. So along with this, we're trying to let users make changes to prices or rates or mixes. And effectively, we're going to keep increasing the capabilities of this. And it's based on customer requirements. We're trying to change quickly. So we need this low latency for lots of data and high capabilities. So what have we tried? We were originally in PL SQL, and this was fine for very fixed schemas and not much advanced capabilities, but we want to start increasing how fast we can iterate on our models, iterate on performance issues, and so we're scrapping the database. So let's try Java, Scala, Python, or R, and turns out that they're either slow or they're not very easy to use and to develop rapidly on. So introducing Julia. We found that Julia really is high performance. We prototyped something very quickly with the help of Julia Computing at the time. And ultimately, we got this into production. And we were over the moon, super excited. So this is our discovery of Julia in 2015. And so I want to talk today about the high-level architecture of this application. We're going to talk through some key packages that make this application come alive, as well as some effective Julia usage that helps with real-time applications. And then we're going to think through and reflect on how can we use Julia at your company, and finally wrap it up with some Q&A. So again, this is high-speed Julia. We're working with a national hospital system tracking 20 billion in annual revenue, and we're doing this real-time speed of thought scenario modeling. So we partnered with Julia Computing to produce the package JuliaDB. This was created in 2015. It eventually did become defunct in 2020, and so we did move to data frames at that point. But this produced the impressive real-time performance that we were hoping for. And this application is still in production today. So this might be one of the oldest Julia applications in existence, which is kind of fun to think about. And we've been continuing to enhance it over the years. So we're excited to reveal this more today. And to note, this application is not just, I'm running a Julia script here, a Julia script there. It's not just running stuff in the REPL. This is something that needs to be low latency, very available for users, and ready to iterate on data changes as quickly as possible. So here's a really high-level architecture overview, a little bit simplified. We're just using an HTTP server. Nothing fancy here. And I know that there's talks at previous JuliaCons and even this JuliaCon about the speed of HTTP, and I'm assuming at some point we'll get something better. But for now, this is fine for our use case. And when we query this backend service, we're getting to either read the data, maybe do some filtering and joining, or we're updating the data. And so we're making the appropriate calls to remote channels to do this kind of work. Or maybe we're changing the state of our application. We're saying, hey, we're locking this data down for this specific user. We're not letting anyone else use it. And generally just some other state management. So all of this is using dataframes.jl workers, and we've distributed them across upwards of 50 workers on production. And we're loading up data specific to whatever scenario we're working with. Maybe it's a budget for a very specific hospital system in Illinois, and we've loaded it up, and now we can run queries, updates against this data. And again, we're not using a database because we need fast performance that we're not able to get with the solutions available. So we're just reading and writing to file system. The only other thing I want to mention is we are not distributing the data across multiple workers in this scenario. We found that it was most helpful to stick exactly one data set on one worker at a time. That just seemed to be the best way to manage garbage collection. That happened to be one of the hardest problems for us moving from Julia 0.6 to 1.2 is garbage collection and compile time. And so sticking to one worker was a way that we were able to mitigate these kinds of issues back in the earlier days of Julia. So some key packages. Of course, we're using distributed. We're using a remote call fetch. And it's very easy to say, worker 8, I want to give you the Illinois data. Let me go ahead and load that up and do the appropriate queries. And of course, you can take advantage of threads on particular workers when that's available. And especially now in Julia 1.9 and above, we have access to better garbage collection that's multi-threaded. And I assume that over time we'll be able to use threads more often. And again, we're just doing the simple features of HTTP.jl. Because these queries take quite a long time, the overhead of using HTTP is very small relative to the kinds of database operations that we're doing. So again, we moved to data frames, and this is just as fast as the initial JuliaDB code. Not many people have probably used JuliaDB in this room, but it was very compiled down to the exact columns and data that was being used. And so that's why it was really fast. But when you start using 5 columns instead of 4 columns, now you have to compile a whole new method. So that was a unfortunate compile time problem that was solved by using data frames in this case. And of course, the more rows you have in data frames, the more often you're going to be able to take advantage of threads. And we added on the mempool functionality that was already in JuliaDB and some of the other highly distributed Julia packages to be able to do the out-of-core processing that is not available by default in dataframes.jl. And then for our file system I/O, we're using Parquet 2. And so the data compression and performant reads and writes were what we needed, but we had to limit it generally to using one thread at a time. So instead of using csv.jl, we were able to use Parquet, and that was faster generally than CSV reads and writes. So a JuliaDB dataset, which is like a serialized Julia file, was about 7 gigabytes, while the Parquet file is about 1 gigabyte. So now for some important tips on using Julia for a backend service. There's a lot of great features in data frames, and especially as we've gotten into the 1.0 era of dataframes.jl, it has been both stable and highly performant, which has been awesome. So if you don't normally think like a database, which most people in here probably don't unless you're a programmer, you think about big tables and you're saying, I want to select these columns and I want to do an operation on the entire thing as opposed to one particular row I want to do a for loop on. And generally thinking through code in this style has been highly effective, especially for memory usage. When we're talking about basically terabytes of memory allocated for these data sets, you're using way less memory allocations, specifically the number of allocations used when you're thinking like a database, because a database, that's all it does, is it always thinks in big columns all the time. And so this is super important for especially this medium to large data modeling and analytics. So think through data in basically the data API.jl interface. So some of these methods are actually not in the in the interface, but they're still database-like operations. So instead of saying filter in a database, you're saying subset. Group by is normal. Transform is specific to Julia, and this is a great feature that you can say, oh, I want to add this column or combine these columns together to make a new one. And then, of course, the joins in place and out of place. So this has been effective not only for this application, but for multiple applications that we've been creating and maintaining for other users in the past few years. My second tip that's important is when you have lots and lots of requirements that keep piling up, you're going to need to continue to iterate on them quickly. And Julia, by far, from what we've found in our experience, is one of the best programming languages for prototyping. So continue to use the Julia REPL or use the VS Code extension, being able to run your code little bits here and there to test your code live against your data sets. And if you've never checked out Revise before, this is a very important package in the Julia ecosystem to be able to set up your code, make changes, and there's plenty of documentation and talks on how to use Revise nowadays, so those are easy to Google. And this was already talked about, I believe, by Sam yesterday at JuliaCon, but focusing on interface development is really important. We want to talk about verbs like create or run or something that really describes your data, like calculate variance or these words that make something click in your brain that say, oh, this is what I'm building, this is similar to the customer requirement, this is similar to what the user is actually doing. So with these tips in mind, this will really help you iterate on a brand new either greenfield project that you're writing in Julia, or it could be some existing code base you're translating to Julia, thinking through your code in verb form. One other really important thing to think about when you're working with Julia is, of course, the just-in-time compile. And when you're working with a web application, that is literally the antithesis of web application development, is you need that first query when the user runs that endpoint to be fast, and by default, that is not the case in Julia because we need to compile this method, compile that method. So we need to think through critically, how are we going to get around this problem? Really, it's a help that we have very fast code, but we got to get around the compile time. So pre-compiled tools, that came out, I believe, last year. Looking through the documentation and talks on that is very important to set up your code base in a way that takes advantage of those tools. You can also create a sys image using package compiler. You can check out the documentation for that. That's where you're packaging up all your libraries, your packages together in one image, be able to load it much quicker. And generally, you can get compile time performance there. And another way is just creating a warm-up script. Go through all the endpoints that your users would normally use and just put in some real data. And now you've already taken away that problem of, hey, is this first query going to be fast or not? We know for sure it is because we've run it already. And then there's some smart architecture decisions you can make to keep workers warm in a sense. So maybe when you're not working with that many users, restrict your user set, your worker set that's being used, and you'll always have your compilation cache ready. Okay, optimizing memory usage is super critical, again, when you're using lots of memory. So I love this optimizing serial code article by Chris Rakakis. It's on book.sciml.ai, and that's been one of the most helpful tools that I show to developers or customers to say, hey, this is how you write really good serial code in Julia. And it kind of teaches you some computer science concepts too. So these are just a smattering of some ideas that are written out there, like avoiding cache misses and iterating along columns, the way that memory is allocated. But ultimately, you're trying to avoid as many heap allocations as possible. There's allocations on the stack that are very cheap when you create and stop a call stack, but anything you're using with dynamic memory, meaning something you don't know the size of at compile time, those are the things you want to minimize. So either you can reuse the same variables or using fused broadcasts, those are the things that you want to think about, trying not to copy your data everywhere when you're calculating and producing the output that you need for users. Using views is another great example. And this is a really simple example of type stability. It's kind of comical, but it's also critical to think about, can I have my Julia types as concrete as possible? So that way when I'm operating on large data sets, I'm able to be in a type stable mode where the compiler can do much better. So instead of a vector of any, this trivial example would be better to have a name tuple where you've got a string and a float as opposed to a collection of data that the compiler can't inference. So to recap, these tips are what we followed, these 5 tips, and that's gotten us to a place where this app is in production, steady now for 9 years, and we've been able to improve performance and stability, and we've moved, we're probably one of the few people that can say that we've migrated legacy Julia code to modern Julia code, but we've migrated from JuliaDB to data frames, and now we're set up for future cloud usage, getting to start using all the capabilities of that to increase performance even more. And I expect as future compilation and memory tooling is available in Julia, it'll get even easier to create really heavy data applications that are also performant and stable. So these are tips that have worked well for us, and they will continue to work well for other applications. But now it's your guys' turn. How will you use Julia? Will it be for engineering or for some science? Is there an application that makes sense for you? Are there day-to-day business operations and number crunching that you can do better in Julia? Is there a greenfield project that you're thinking of that you've been wanting to do? You can't find the application, the right architecture. Or maybe there's some data science that you've wanted to do and you're kind of tired of Python, or you think that there's probably a better way, probably more performance I can eke out. See, the sky's the limit with Julia because of how quick you can iterate on development, how quick you can prototype, and how high performance it is. It really is the best language in 2024 to be using for greenfield development because there's nothing else that you can grab all these different packages together and produce something that's never been done before, like what we did with this financial application in 2015. So just to give your appetite a little bit more to chew on, this is another business analytics case study, specifically from 2022. So there's a popular airline in the US, and they contracted us to make a dashboard application to aggregate and do some analytics on some flight schedule data. And so we started development, and it was just 8 weeks that it took to get actually to a place where we're in production, which was great because it was 3 times faster than they were expecting us to be done. And this is because Julia is fast to develop in. And the faster you are at Julia, we actually didn't even need all of our developers. There was 4 times less budget than what we were expecting, which is great, This was not something that was going to be possible in Python because it was just going to be slow. It was not going to be real time. It was not going to be something where you can see the analytics in just a couple seconds. So of course, what do you do with your remaining time? You just make it better. You just do something that's never been done before. So they were set up well for the next version. And if you're looking for what packages we're using and kind of how to do this yourself, maybe, we use DB interface to pull from the database. Of course, we're using dataframes.jl. And there's some nice plotting utilities. If you've never checked out the plotting libraries in Julia, Plotly.js is a great library for that. You can make things really interactive. You can download, and you can kind of crop and make edits to the view of the plot. We ended up using Stipple and Genie framework for this one, and that was really effective to be able to just wrap everything up all together. It was a nice, clean interface, and we just got to do everything that we needed to really in 8 weeks. And so this was successful, again, because prototyping was very simple in Julia and it was high performance. I'm just going to give a smattering of a couple other industries that we've touched with differential equations, and these are some of the packages that we've used. But effectively, we have success stories of moving things from MATLAB to Julia, whether it's 1,000 lines or 10,000 lines or more of MATLAB, and computational fluid dynamics, thermodynamics, macroeconomics, pharmaceuticals. But really with Julia, the time is now to start developing. There's so much you can do to advance your business. So just take a step using Julia. Just start with your next greenfield project. Get ready to develop that back-end application that you've been wanting to do to create value. So we have a Julia Basics blog series on our website, and our website's got a QR code there, but that's what I want to talk to you about today, is getting ready to do Julia in 2024. And I'll take any questions.
So are there any questions? Very quick.
Yeah, so I was wondering, you started out in Julia 0.6, so even pre 1.0.
Yeah.
How did you distribute Julia, like an application back then? Was it like, and did that change over time? Did you choose a different way of distributing?
Yeah, there is, I think, 5 different iterations that we had of our architecture. It really does make a lot of sense at the end of the day to just keep all your data on one process when you have this much data. If you have less than terabytes of data, maybe you only have like 10 gigabytes of data in memory, maybe you can just stick to a couple worker processes instead of only using distributed. But yeah, our data size, it just made sense with garbage collection. And this was before threaded improvements to garbage collection too. So it really just made sense, separate Julia processes so the garbage collector can run as needed.
I'm also interested in how Julia was, so did you run it on the web, or did you have a distribution that you provide? Okay, so you ran it on the web, so it was running on a server.
It was on a server.
Yeah,
It was on a server. Yeah. We just started up Julia in, an infinitely running script. We're just continuing to run the HTTP server until we quit it.
Okay, clear.
Yeah.
Thanks. Yeah.
Yeah.
Any more questions from the audience?
Hey, thanks for the talk. Just a quick questions. I was wondering of any consideration about the usage of Parquet as opposed to perhaps Arrow formats, and whether there were considerations on the I/O from not using an actual database and by potentially reading large chunks of data rather than being more granular. So I don't know if you could provide some clarity on there.
Yeah, sure thing. I believe when we did our performance testing, it just happened to be that Parquet was faster, single-threaded versus Arrow. I think Arrow might probably be faster when you have multiple threads, but we are kind of constrained to using one thread. And then as for, splitting up the data into multiple chunks and loading, that's another thing that we had considered. That's actually really effective when you're using D-tables, is kind of splitting everything into different chunks and pulling it all together. So in our use case, it just happened to be faster when we were prototyping to do it the way that we did. But your mileage may vary. Honestly, it could be better splitting things up.